Right. So today I'll talk to you about a novel proof technique. This is joint work with Roberto Blanco, Jeremy Thibault, Adrien Dourier, Deepak Garg, and Catherine Ritko. So by the end of this talk, you should be able to understand what I mean by data flow back translation, hopefully. So the general setup we're working in is secure compilation of partial programs. And the emphasis is on partial. And the risk here is that these partial programs, after being compiled, they may be linked against context that could be buggy or malicious. And the strategy to mitigate this risk is to compile these programs properly, meaning to have them be protected from the context and to prove that the partial programs are secure, meaning they are protected from the context. So as an example, I will use a single modular compilation unit as an example of what I mean by a partial program. So here I have this example, which consists of a main module that imports a networking module. The main module is the partial program, and it calls the init network function, which is implemented by the context, which is the networking library. And notice that the partial program intentionally shares some memory with the context. So it shares this array IO buffer with the context. And notice that there's also some other memory that it never shares with the context, namely this user balance variable. The intention is that this user balance is high integrity. And recall that the risk is that the context is buggy or malicious, which means that it might access the user balance against the intention of the partial program. Namely, it could, for example, take this argument of the init network function, which would be a pointer to the array, and it could increment it past the bounds of the array and store something to override, store some value that would override the user balance. That would be bad. And the idea is that we could rely in principle on compiler enforcing fine-grained memory isolation, for example, by relying on cherry or micro policies and so on. I will not focus in this talk on any concrete isolation mechanisms because the languages we model are more abstract. Instead, I will focus on proof techniques. How do we prove that the partial program is secure? In particular, I would like to prove something that says the security of the source program part, assuming a memory-safe source semantics, is preserved after compilation. So for our particular example, we would like a statement like this. If no execution of the source program part with a source context overwrites the user balance, then also no execution of the compiled version of the program with a target context overwrites the user balance either. And more generally, we would like to prove a statement, such a statement for all safety properties S. If no execution with the source context violates S, then also no execution of the target context violates it either. This statement in particular is called preservation of robust safety and is familiar from lots of secure compilation literature. In this talk, I will explain a proof technique that is called data flow back translation. And the key benefits of this proof technique is that it is suited for languages with memory sharing and not just languages that interact in more primitive ways, in which program parts interact in more primitive ways. That we have tested this proof technique on, they are syntactically dissimilar, meaning one language has unstructured control and the other has only structured control, the source language. So back to our desired statement, I will just put it in the contrapositives, which is nearer to how we actually prove it. So if there exists an execution of a target context that overrides the user balance, then there also exists a source context and an execution in which the context overrides the user balance. So this is essentially just a reduction of the insecurity in the target level to insecurity of the source program. Like this translation of a target context to a source is called a back translation, and it's also a familiar problem from plenty of secure compilation literature. And the way we prove it is by using a strategy by Abati et al. 2018 paper, which essentially is a back translation lemma, but about just whole programs, not about an arbitrary partial program. So if there exists an execution for a whole target program, then there exists a whole source program and the related execution. So broadly speaking about the back translation, in general, there are two techniques, or I would like to view the literature in secure compilation as presenting two general techniques. One is syntax-directed back translation. Here, we'd like to write a function that takes a target program, produces a source program, and notice that this function should work for all target programs and not just the image of the compiler. So this problem is different from the inverse compilation problem. And then we'd like, of course, to prove that this function that we've written is correct, meaning that it satisfies the spec above. So the good news is correctness proof would usually be similar to a compiler correctness proof. So familiar from compiler verification literature. The bad news, though, is that if we have a target language that, as I said, has unstructured control and the source only has structured control, then it is not clear how we can write such a syntax-directed back translation. We can rely on heuristics, but they would be incomplete, or if they were complete, they would involve complex transformations. Trace-directed back translation tackles this problem of syntactic dissimilarity. It ignores the given program, focuses just on an execution trace, meaning an individual run of the program. So we are given an interaction trace, and we would like to find the source program that just witnesses this one trace among all the traces that it has. So we're given a prefix of one target trace. The advantage is, of course, this is indifferent to syntactic dissimilarity between the target and the source. The reason is that the model, the interaction trace model, it only mimics the external interaction and it ignores the within module control flow. Bad news is that correctness proof here is usually more involved, especially with features like memory sharing. And this is what I will explain next. Why is it more involved? So essentially, it's more involved because of lack of information. But what do I mean by that exactly? So we are given a trace that is emitted by a target program. We want to find a source program that emits a related trace. By related trace, this will mean in the existence of memory sharing that the back translation has to also mimic the visible shared memory operations in order to be able to actually emit a related trace. How is that so? It's because these are traces of externally observable events and memory appears on the externally observable events. Let me just explain this alphabet a little bit. So here there are these silent labels, but these we just ignore. We eventually drop them and we end up with essentially the calls and the returns. The calls, there are two kinds that I have here. Border crossing, I'm calling them border crossing call events, program to context and context to program, and similarly for return events. But most crucially, these calls and returns record a snapshot of all the memory that is shared so far. And this is the key reason for the difficulty recording this memory and trying to mimic it in the back translation construction. This is the difficulty of why the trace-directed back translation proof arises. And I'll walk you through the example to make this point even clearer. So I walk you here through one possible execution of this program. Remember, we have these two border crossing events, these two border crossing calls to init network and the receive function. And then we also have these memory regions, the orange one for IO buffer, the black one for the user balance. And because we share the IO buffer, this is the region that appears, it's a snapshot of its contents, appears on the trace, the call to the IO network, to the init network function, and also the return event from the init network still shows the IO buffer with the same contents. And now this receive, the call to the receive function, even though it doesn't really directly share anything new, but still the contents of the IO buffer will appear because they have been shared, because the pointer has been shared already before. And now something interesting could happen, which is that, well, the receive function executes and then it takes some data from over the network and it populates the IO buffer with this received data, which I'm denoting here with the green color of the IO buffer contents. What does this mean, the behavior of this receive function? Well, it must have meant that the init network function must have stashed the pointer to IO buffer somewhere in memory in order to enable the other functions of the networking module to access the IO buffer. And it's this stashing behavior that is really the origin of the difficulty of the translation when we have the traces. And the reason is that this stash doesn't really appear on the interaction trace because it is not part of the shared memory. But at the same time, the trace-directed backtranslation still will need to somehow find a way, like produce a source program that also finds a way to enable the other functions of the networking module to access the I/O buffer, which means the trace-directed backtranslation implements its own stashing behavior without relying on information from the trace. And what previous work, well, by myself actually and other collaborators, what we did to overcome this, like to basically mimic this internal behavior, is we traverse the whole shared memory graph. So we have the graph, which is the shared memory, which we have on the trace, but we need to traverse it, and we need to stash it in the private memory of the context. This stashing means we have to flatten the whole graph and to basically store it in some private variables. We have to maintain invariance between the flattening and the original graph and so on. The problem is that such stashing mechanism it was done, it was a paper proof. When we try to mechanize this proof, it isn't very easy, because we have to prove termination lemmas and completeness lemmas about graph traversal algorithms, and this isn't really like a nice way to do things in Coq. So we thought maybe there is really a way around this stashing of pointers. So far, what we need is a back translation technique that will allow us to support memory sharing that we can mechanize with reasonable effort, but that is still indifferent to the syntactic dissimilarity between the target and the source. That was the whole reason we looked at trace-directed back translation. And I'm claiming that DataFlow back translation, the novel proof technique that I'm presenting, has all of these three advantages. So the high-level idea of DataFlow back translation is to make the traces more informative so that trace-directed back translation becomes easier. Here we actually need to be a little careful, because if we change the trace model, this might mean that we end up with a top-level statement about a different trace model that now makes the theorem statement itself invalid. But thankfully, there's an easy way to sort of decouple the two models to have the interaction trace model and then the more informative data flow trace model. Now, so what is this data flow trace model? So recall the alphabet of the interaction traces. There was these silent labels that denote internal execution. This is the problem. The problem is they are too abstract. So they do beneficially hide the control steps, but they unbeneficially hide data flow steps. So we selectively break this silent label abstraction by introducing more informative data flow events. And these events, they essentially mimic operations of the target language. And in particular, they are emitted by any step of the execution of the target program or context that modifies the memory or modifies the register file. So for example, if the target context stashes a pointer or recovers a pointer from the stash, even though these are internal steps, still the data flow events will now reveal these operations that constitute the stashing or the recovery. And with these events in hand, we have now, we can write a back translation function that takes data flow traces input and produces a source program. Let me give you an example, a concrete example of possible stashing behavior. So the target context stashes the pointer that is stored at shared address A+5, say in a private address B. Remember, on the interaction trace, this whole operations will just appear as the silent label. However, with the data flow model, there are some very informative events that will appear. So assume on the right here, this is the state of the register file. And so this is just one possible sequence. There will be a move event that takes the argument, puts it in R1, and then we put the value 5 in another register RCT, and then we add this to R1, and then we load the actual pointer, this one that we want to be stashing, and then we store it in the private memory, B. So with these events in hand, we now can back translate these events into a source program. The idea is to reserve one fixed source variable to simulate each target language register, and then step by step we can have basically the move operation, move the argument into the temp1, which would mimic the R1 register, and so on. The constant operation is also an assignment. This is the bin op, and so on. So the benefit is stashing pointers is now for free. There is no need to implement a traversal of the whole reachable memory or anything. And also here, the source variables, they very closely mimic every change to the target registers and to the private memory, which makes the simulation, the proof of a simulation lemma between the execution of the source program and the given data flow trace a much easier proof. So in summary, DataFlow BackTranslation supports memory sharing without the need for graph traversal, comes with a mechanized BackTranslation lemma in COP, and it works for syntactically dissimilar languages. So it shows a target language with unstructured control and a source language with structured control, even though both are really safe and untyped languages, but we're focusing on this syntactic dissimilarity issue. Okay, there is more in the paper that you can read if you are interested in the technical details. And just to highlight one more thing from the paper, our secure compilation proof allows also reuse of whole program compiler correctness lemmas. This is enabled by what I'm calling a novel turn-taking simulation relation. So just very quickly to motivate, why do we want to reuse whole program compiler correctness lemmas? Well, in any case, some kind of correctness obligation usually shows up in a secure compilation proof, and proving such correctness of a compiler, this is years worth of manual proof effort. And okay, why whole program compiler correctness in particular? Because whole program compiler correctness makes no assumptions about the context, unlike, for example, other partial program compiler correctness results. And making no assumption about the context is important because there will be no difficulty in instantiating the whole program compiler correctness lemma. All right, so that was it for me, and happy to take any questions.
Okay, so hello?
Hi, yeah, I can hear you, Jonathan, when you're unmuting.
Hello?
Hi, yes, I can hear you.
We're having some technical issues here with the sound, but let's try to take some questions.
Yeah.
From the online audience first, if we can.
Right. What if the source language doesn't have arbitrary pointers, just objects or references? Can it still simulate machine level memory writes? Yeah, that's a good question. So, our source language doesn't have a way of forging pointers. So it basically has to. So basically, what happens is that the intermediate steps they basically get tracked through the variables that are simulating the registers, and the accesses to the memory they happen all with reference to the base register in which the pointer was living. And this base register then, well, it starts from an argument to a function, which is also something that's not a forged pointer. However, I guess the question is about what if the language is high level, like maybe something like Java, and it doesn't even have a notion of pointers, so it's not a language like C. So I haven't given it enough thought, but I would say a priori that if the compiler were secure to begin with, in the sense that when it allows linking with target contexts, then there is a way to protect rights to, for example, private fields of an object. Then there should be a way, I guess, to be able to perform such a backtransslation. I'm seeing Marco Patrignani commenting, and he has done some work on this in the past. The source has objects and targets authorized chances that the trace model is different already. Yes, so it's either that the trace model, yeah, exactly, yeah. So it's either the trace model is different already, and then that manifests. So then your question is then manifests as the proof burden of how to actually relate traces. What does it mean even to relate traces? So that's one thing. But even if we find a way to relate traces, then this way should be informed by the enforcement of the protection of private fields of the object. And it's that enforcement that enables us to actually find the proper back translation function. I hope that makes sense.
Okay. Hello? This is going through. Okay. We have another question from the in-person audience from Leonard.
Yeah, just to expand on this a little bit. Is there any complication if you want to map back locations that come not from the heap, but say from the stack that was only materialized during compilation? Or do you need to have any control over what happens to the newly introduced variables in the source language? Then how they would be treated by allocation, register allocation, or so. And just in general, this kind of similar question arose in the development of compositional comcert and its extension to concurrency, where we had sort of, I think we just traced the set of accessed low-level locations and mapped them back already, but it was clear that it can be done for the sort of traces in a little bit more intentional way as well. So I was wondering whether you can compare to that as well.
Yeah, that's a very good question. So to be honest, so first of all, in our languages, the model of passing arguments is very primitive in the sense that we don't even pass arguments on the stack. There is no notion of a data stack. Okay. However, to answer your question generally, just without having spent time on technical details, just speculating here, I think what would be missing as piece of information that is needed, along with the trace as input to the back translation, is an understanding of what is the view of the context about the arguments and about the stack. So basically, you need some layout information as input, not just the execution. Where basically there are some loads and stores, and there's no understanding of the mapping. Yeah, I hope that makes sense.
Let's thank our speaker again. We might have time for one quick comment or question. Yes.
Can you hear me? No?
Yes.
You can hear me. Great. Nice to meet you, Akram. Thank you for your presentation, and nice to see you again. So very quickly, you said you back translate interaction traces. Does this mean that you translate only or try to find a suitable source program that generate these traces? So you back translate the traces that only come up when target programs interact with sort of context or any sort of target level traces.
So what I meant by interaction traces are the traces that record just the interaction between a program part and the context, or basically just the interaction between the component, the inter-component interactions, but not the intra-component interactions. Actually, that's what I meant by interaction traces.
Okay, so that's great. It's not just any old trace that might come up on the target level behavior. I think that's good, okay. And as a rule of thumb, how much similarity to the kind of behaviors in terms of traces that the two languages have to exhibit in order for this method to be able to work. If you can give me that kind of.
So you mean the DataFlow back translation method?
Yes, yes.
Yeah, I guess that is a little similar to Xavier's question, and I guess it's a similar answer in the sense that I haven't given it enough thought yet. So yeah, sorry about that, but yeah. So yeah, I just
Okie dokie.
Maybe I think about it more, and then we can talk about that. Sorry. Yeah.
Okay, so we're a little bit out of time, so let's thank our speaker and move on to the next talk.